Yep. All right. So I got a brick here, and a lot of times when I talk with students, I talk about it as the baby with a brick problem set. See this little baby down here with a brick? I talk about my own life sometimes. My grandfather used to give me his bricks to play with, and I only had to have one operation. But I was this baby with a brick. Okay? So this is autobiographical. Baby with a brick. But let's talk about what's going to happen if you slide this brick. If we go back to the kid pushing the chair. Remember we had the kid pushing a chair with 15 newtons? Pushing this chair with 15 newtons, and there's always going to be somebody that says, what we need to get there? Is there Rebecca will say a reference frame, right? So we're going to throw in a reference frame. We'll make there be an up and a down. We'll have a right and a left, and we'll give it a positive and a negative. Sure, why not? That's all good. So we'll do that. We'll get that business out of the way right away. But it says here that I have a coefficient of static friction and a coefficient of kinetic friction. And if you're not quite sure, that's a typed letter mu and a typed letter mu. Those are both mu's, okay? So that's mu s and mu k, coefficient of static friction and coefficient of kinetic friction. And the first question is, what's the Fs? What's the static friction force? Well, this isn't so bad. Fs is equal to mu s times F normal. And as I inspect this startup of a free body diagram, I can see that the F normal is 200 newtons, and I can see that mu s is 0.05. I don't feel bad about that. 0.05 is 5%. I know that 5% of 100 is 5, and 5% of 200 is 10. Yeah, so that's just my quick head math, okay? I always like to use head math when I can. Keeps my brain working. But something about this friction, look at the reference frame. What's the static friction value in terms of the reference frame? What have I missed? Negative. So you know what? This is an annoying thing where my thinking brain has to be thinking and insert that negative sign because it doesn't get inserted by any other means. So that 10 newtons is to the left. I said, okay, well, that's great. Done. I'm not going to do therefore statement or anything. I'm just going to keep on moving and try the next one. Yes, sir.
So I put left as positive and right as negative. It's like the exact same.
Yeah, if you make your left be positive and your right be negative, that's your business. Yep. Yes. Sorry? Well, friction isn't always negative. Friction points in whatever direction opposes the motion. And in this case, I thought, it makes sense to me that the applied force is going to be positive. I'll let the friction be negative. Just because that's how it sits into my brain nicely. And I think a lot of people's brains work that way. All right, so kinetic friction. I've got my mu k times F normal. I'm just answering simple questions. I don't have any fancy plan or agenda yet. And I say, okay, well, mu k was equal to 0.0400. Normal force was equal to 200 newtons. Reminder, mu k doesn't have units, and we're all cool with that because it's just a ratio. 0.04 times 200, that's 4%. So 4% of 100 is 4. 4% of 200 is 8. Yep. So we get 8.00 newtons. What did I miss here based on my reference frame? Negative, yeah. So I'm going to force that in with my thinking brain. And I say, okay, well, then that is going to be 8.00 newtons. Maybe I'll even color code it. That negative sign becomes left. Okay. I haven't even really done any problem solving yet, except when I look at this, it says find the net force. And when I try to find the net force on this, I got to ask myself a question. Either this block of wood is sliding or it's not. So I want to ask myself the question, is the block sliding? Yeah. It looks like from the arrows that it is. Can anybody offer me some numerical evidence? Yes, sir.
Since Fs is 10, it means that it's at least sliding at 5 newtons.
Right. So it looks like Fs is 10 and the applied is 15. So it looks like we're overcoming static friction. So I'm going to express this as an inequality. I'm going to say, all right, well, that means that at least the absolute magnitude of the applied force, as Alex says, is greater than the static friction. And if that's the case, if that inequality holds true, so this is an if-then statement, so I can say if, then the block experiences, I like these if-then statements. Seems so consequential. Experiences kinetic friction. Now, if you're going to say that it experiences kinetic friction, doesn't that mean automatically you should ignore static friction? Because this block is either sliding or not sliding. And I can't tell you how many times I've seen people have a block that slides and it's resisted by both of these forces at the same time. That can't happen. It can't be sliding and not sliding at the same time. So I'm just going to put it out there, ignore Fs, because I don't want anybody to fall into that trap of saying that it's going to experience both at the same time. It's an either-or situation. It's either sliding or not, okay? So then I say, all right, well, F net is equal to F applied plus Fk. And I can sub in my values because I've already done the calculations on this, 15.0 newtons plus, and again, I'm still emphasizing reference frame negative signs, 8.00 newtons. And of course, 15 plus negative 8 is 7. Now, strictly speaking, since this is a simple addition problem, I got to look at the lowest number of decimal places. So 15.0, the 0 is the lowest number of decimal places, so it really should be 7.0 newtons. Just because it's its own isolated little problem. You got to follow those decimal place rules. And since it's positive, I could say that it's to the right. Now, there's not a part D to this. But if I was going to find a part D to this, I might ask, what's the acceleration of this system? You know? And if I wanted to find the acceleration of this object, I'd have to know, well, you know F net for a system is equal to the mass of that system times the acceleration of that system. And so the thing that I'm missing right now, because I've got the F net, the thing that I'm missing is the mass of the system. Can you see that? I mean, I know that I could rearrange this thing. I could get acceleration of the system is equal to F net over mass. There's no doubt about that. But what's the mass? Well, you know, we're not going to do part D, but I'm telling you this because it might show up in the homework. Look at this. If I know Fg is 200 newtons, don't I also know that Fg is equal to mass times acceleration due to gravity? Doesn't that mean that I could say the mass of this thing must be 200 newtons divided by 9.81 meters per second squared, if 9.81 is the acceleration due to gravity? I'm not even going to take this to completion. I don't want to say it's beneath us, but I just want to put it out there that there's a roadmap here, okay? We could calculate this mass, we could put F net and the mass value into this expression, and we get the acceleration of the system, okay? I want to move on. I want to talk about babies with bricks, okay? I think we can all agree on that. This is the important stuff. We got this baby pushing on a block, and you know, I've seen different versions of this. I got sort of a, I don't know, this problem that lacks personality. There's an applied force there. But we could say, hey, this is the applied force, like the baby, down at an angle. See how this baby would angle their applied force downwards? I've also seen problems in textbooks on the websites where I have people pushing down on crates with an applied force. You see that's all the same thing as the baby with a brick? I like babies with bricks. So I want to put it out there, a few pieces of information. The mass of my brick is 10.0 kilograms. I want to say that that theta value, this angle right here, is 30.0 degrees. So I'll say theta, the angle below horizontal that the baby is able to push with, is 30.0 degrees. And this is a strong baby. This baby is able to push with 100 newtons. Okay? I don't know. I don't have a good sense of whether that's a lot of force. I feel like it's a lot for a baby. Okay? You have to figure that out. Okay? And I think to myself, well, these are all illustrations. I want to do like a proper free body diagram. So I want to like engage with the thought process of how to do a free body diagram. First of all, every brick experiences gravity. That should be self-evident. This is a baby pushing a brick. So the baby pushing the brick has an applied force that's down at an angle. And of course, if I have an applied force down at an angle, it stands to reason that there must be an x component to that force. I'll call it F applied x. And it's going to have a y component. I'll call it FAPI. Right? And as I look at this, Can you guys see that the F applied y and the FG are both downwards? Does that mean that the normal force is going to push upwards with the same force as force of gravity or more? More. It's going to have to work harder, isn't it? Going to have to force harder upwards? We're trying to push this brick into the ground. The normal force is going to be big upwards, right? That makes a lot of sense. And it also makes sense that there's going to be an FK going back like this, working against our motion. All that makes sense. You know, something that I want to lay out here is that F applied x, because the F applied x is the adjacent side of this triangle, I would say F applied x is equal to F applied times, you know, I didn't budget for space here very well. Let me just clear myself a little bit of ground. Oh, what happened to my tape? Oh no. This is the day where my whiteout broke. You were all here for it. All right, so let me just get rid of that, get that out of the way. I would say that F applied x is equal to F applied times, because it's the adjacent side, cosine of theta. And F applied y, because the applied is the opposite side, would be F applied, the hypotenuse is F applied, times sine of theta. This is just SOHCAHTOA ratios, right? So we want to be good at that. We want to feel comfortable with that. And I'd like to take a look at this as a system of equations. So the first equation that I want to look at is the y thinking. And in the y direction, I would say F net y is equal to F normal plus Fg. I'm pulling this off of the free body diagram, plus F applied y. Before I go any further, are any of these values 0 for a baby pushing a brick across a horizontal surface? Is the brick going to fly into the air? Is it going to crash through the earth? What's the brick's acceleration vertically? So F net y is 0. Okay? That's a nice special case about sliding things across horizontal surfaces. Okay? That's important for bricks. It's important for lots of situations. But that would mean that 0 is equal to, and I'm going to write F normal, but don't get ahead of me on this one. I want to try something different this time. Is Fg up or down?
Down.
Is down going to be positive or negative, do you think? You know what? How about we do this? How about we define our reference frame, up, down, to the right, and to the left. Let's make down be negative and up be positive. We'll make right to the positive and left be negative. How about this? Before I even sub any numbers, some people like to do this. This is a slightly different twist on style. I'm going to force in a negative sign so that I don't have to think about it later. I'm going to say F normal minus whatever the value of Fg is. And then is F applied y up or down? Down. It's down. Look at that. Fappy is down. Look at the picture. F applied y. Now, there are some purists out there that say you should really put absolute values around those guys, and that's fine, okay? But, you know, we were trying to find the normal, we're trying to find the normal force. That's what I want to get right now. So I would say, okay, well, normal force then, hey, look what happens. When I take those negative signs over to the other side, it becomes positive Fg plus F applied y. And then when I go to sub in my values, well, you know, I think I'm going to write Fg as just mass times acceleration due to gravity. And I think I'm going to write F applied y. Didn't we already say it was going to be F applied times sine theta? See that there? And then I can sub in my values. What was this? This brick was 10 kilograms. And acceleration due to gravity is 9.81 meters per second squared. Now, have I already dealt with the fact that gravity is negative? Yes, I have. So I don't do it a second time. Okay, I'm not going to deal with it when I sub in the values this time. I dealt with it in the formula stage this time. I wanted to try something different, okay? But you can't do both. It's an either or, okay? So plus F applied, and F applied was 100 newtons times sine of 30. And I believe you guys can do this math. I worked ahead on this one. I got 148.1 newtons. Anybody want to confirm that one? Double check. Don't trust me just blindly. Did I get it right? All right, I've gotten 2 nods so far. So I'm going to accept that we got that guy. And then I want to say, hey, that's kind of the end point for talking about the y information. Let's talk about the x information. In the x direction, f net x, let me just pan back up here to my picture again. See that f net x is just going to be fk plus f applied x? That's all the information in the x direction. So I'll pan back down here. I can't keep everything on the page at the same time. That's a challenge. F applied x plus fk. I can expand that out. Remember we said, I can keep this on the page at least, f applied x was f applied cos theta. So I'll expand f applied x out to f applied times cos theta. And when I put in my fk value, is the fk value going to be a negative value or a positive value? Negative, right? So I'm going to put in my negative sign now, just like I did with the y stuff. And I'll say minus mu k times f normal. And as soon as I put in that f normal, you're like, oh, that's why he needed to get the f normal first, because it's going to be a part of what's happening in the x direction. It's a system of equations. So we haven't subbed any values in yet, but I'm going to take an arrow and pop back up to the top over there and start subbing in values now. F net x is going to be equal to, okay, F applied, 100 newtons times cosine of 30 degrees minus mu k, which was, what did we say? Did I even say what the mu k was for this? Oh, let's say that now. I don't think I even said it for this baby. Let's make it be mu k is equal to 0.500. 0.5. I never did state that. All right, well, that's good. We got that now, at least. 100 newtons times 0.5 times the normal force, 148.1. Remember, I don't want to prematurely round anything. And I get something that rhymes with 12.
What is the mu force?
What is the mu?
Yeah.
The mu is the coefficient of kinetic friction.
But did you put down a number somewhere?
It's 0.5.
Okay.
Yep. What'd you get? 12 point something or other? Oh, nobody did it? Come on, somebody help me out. It's 12 point something. John? 1.55. All right. Oh, that's how I got. Oh, I did get 12.55. You're right. I got 12.5525. Yeah? Oh, yeah. Yeah, that's cool. 12.5525 newtons, and it's positive, so it's to the right. But let's look at the question. The question was, what's the acceleration? Not what's the net force. Ah, shucks, we're not quite done yet. But don't forget, remember, didn't the y components cancel out? So the F net really is just F net x, right? So I can say F net is equal to mass times the acceleration of this system. And so if I want to get the acceleration of this brick, it's just going to be F net divided by mass. And gosh, we already calculated F net. This part's not hard. We did all the hard work. 12.5525 newtons divided by, wasn't it a 10 kilogram brick? It's nice and safe. Move the decimal place over one time. So 1.25525 meters per second squared. Or if we're working with 3 sig figs here, it looks like 1.26 meters per second squared. And it looks like it's positive. So we could even say, I'm running out of space here, but we could say that it's to the right. And that's a lot of figuring. I'm not going to say that it's not a lot of figuring. And I'm not even going to say that it's child's play, but it's definitely baby with a brick. Okay? Anybody have any questions? Yep. Is a baby with a brick a child hazard? It is a child hazard, yeah. It probably wouldn't pass whatever the child safety protocols are.